In this problem, 400 milliliter of 0.600 molar nitric acid with a strong acid is mixed with 400 milliliter of 0.300 molar barium hydroxide in a constant pressure calorimeter of negligible heat capacity. That means here we assume the calorimeter absorb no heat. The initial temperature of the both solution, that means nitric acid solution and barium hydroxide solution. And keep in mind, this is water solution. The majority of the solution in it is the solvent water. Now the temperature of the initial solution is the same at 18.46 Celsius. What is the final temperature of the solution given that the heat of neutralization, i.e. the proton H plus react with hydroxide OH minus to produce water? The heat of the neutralization for this reaction, this is neutralization, the enthalpy change is negative 56.2 kilojoule per mole. This is negative, therefore it is exothermic. And we know the reaction releases energy and releases heat, and the heat goes to actually stays in the solution with the majority part of the solution that's water, and the solution, the temperature of the solution will increase. Alright, okay. Now, I want everybody, when reading this problem, have a very clear physical picture about what's going on. What's happening here is a 400 milliliter 0.600 molar nitric acid solution. Keep in mind, this is 400 milliliter mixed with another 400 milliliter. Excuse me for the stick figures, just for the ease of the writing this things down. Another 400 milliliter of 0.300 molar base barium hydroxide. Now, I want you to see this clearly. After the mixing, we have how many more milliliter of the solution? That's 400 plus 400, 800 milliliter of the solution. That's a very important picture. And for these solutions, 800 and 400, 400, 800, the majority of the solution is water. Okay, right here is water. And don't get confused with this water as the reactant, as the product. The mixture, the neutralization of acid and base only produce the very tiny part of the water. Compared to 800 milliliter, this part of the water generated from the acid and base is very tiny. So therefore, we consider the solution as 800 milliliter of water. Okay, now it is not given here, but we should know that the density of the water is about 1 gram per milliliter, and the specific heat of the water is 4.184 joule per gram per Celsius. But you don't have to memorize this. I can give it to you during the exam or quiz. Okay, now the overall reaction, we can write it down as the balanced reaction is nitric acid react with barium hydroxide. We have barium nitrate plus water. Okay, it's aqueous solution, aqueous solution, aqueous solution, and liquid water. Okay, so from the initial volume and concentration, Okay, we can calculate the nitric acid, the mole number of nitric acid. So let's write it down. 4.00 times 10 to the second milliliter. We convert it to liter. So this times the molarity and give us 0.240 more. Okay, and for the base, it's 400 milliliter times, let's do the conversion, and times the molarity. It gives us 0.120 more. Okay, now let's look at the net ionic equation. Please work offline to make sure you understand that the net ionic equation for this reaction is simply proton react with hydroxyanion to produce water. Okay, so now what's the mole number of the proton? It is 0.240 more. What's the mole number of hydroxide? Okay, for 1 mole of barium hydroxide, it gives 2 more right here of hydroxide. Now we have 0.120 more of barium hydroxide. The mole number of hydroxide is 0.240 more. And there's no limiting reagent. Acid and base will react completely. Now, because we know the molar heat, the heat of the neutralization given here is 1 mole of the proton reacted with 1 mole of hydroxide. We produce 56.2 kilojoule. That's the heat, and it's exothermic. Now, the heat, therefore, the heat of the reaction neutralization equal to 0.240 mole times negative 56.2 kilojoule per mole. Okay, we can do the calculation. It will give us 13.5 kilojoule as heat. Now think about where does this heat go? This amount of heat generated from the mixture of the acid and base will stays in the constant pressure calorimeter because no heat can leave the calorimeter. But the calorimeter has a negligible heat capacity. It means it does not absorb heat. So where does heat go? The heat will be absorbed by this final 800 milliliter solution, mainly a water. So because both the acid and base solution are very dilute, that means most of the solution are water. So here 800 milliliter of water of a solution, we can mainly treat it as the water. 800 milliliter of water with the density 1.00 gram per milliliter and 4.184 joule per gram per Celsius as a specific heat. So to calculate, now we know the amount of heat generated from the reaction. To calculate the temperature rising from after mixing, we need to calculate the heat capacity of the water. So the heat of capacity of water, 800 milliliter of water is 8.00 times 10 to the second milliliter. Volume times the density and times 4.184 joule per gram per Celsius. It gives us 3.2 0.35 times 10 to the third Joule per Celsius. Okay, now we know the total heat generated, and we know the heat capacity of the water. Now we can calculate the change of temperature. But to be precise, let's think about this. If we treat the solution here, and the calorimeter as the system, therefore, because it's a calorimeter, there's no heat exchange between the calorimeter and the environment. So therefore, the total change of the system equal to 0, and the heat change of the system is 0, and the heat within the system is from the reactions, and heat absorbed by the 100 milliliter of water. That's 0. So therefore, Q water equal to negative Q reactions. And also we know Q water equal to the heat capacity of this 800 milliliter of water times delta T. So therefore, change of the temperature equal to Q water over heat capacity of 800 milliliter of water. And from this, water equal to negative Q reactions, and we have the Q reactions is negative 13.5 kilojoule. We have negative 13.5 kilojoule over 3.35 times 10 to the third Joule per Celsius. Then we need to convert kilojoule to joule. For every kilojoule, we have 1000 joule. Then we do the calculation and get the final answer, 4.03 Celsius. That's the delta T, and the final temperature equal to initial temperature plus delta T, that is 18.46 Celsius, plus 4.03 Celsius, that is 22.49 Celsius degree. Okay, that's end of the problem.